Hello everybody and welcome back to a Mathematical Rhapsody. I know it's been about 2 weeks since I last uploaded a video and I'm really sorry about that. And please do not criticize me if this occurs again. But anyways, leaving all that, let's start with our session. In the last video, we talked about electronegativity and electron affinity, right? I told you about the difference between them, and I also told you that we will mostly be needing electronegativity to understand some of the concepts in biology, right? Okay, now let's start with some revision. Not that much, no. But since we're mostly focusing on electronegativity, in order not to waste time, let's just look at what electronegativity is. We saw that electronegativity is the power of an atom in a bonded compound to steal or rob electrons for some time only from uh, the other atom to which it is bonded to, right? It's not like stealing, it's more like having it more around itself, right? If you are a big brother, for example I am, so what happens is you get to keep the toys most of the time, but you will have to share it with your brother, right? But as you become older, you will think they you don't like it and you just give it to your brother and he plays for eternity. Anyway, so that's exactly what happens here in bonds. That's exactly what happens in electronegativity. You have more power over toys than he does. So the toys will be more around you than your smaller brother, if you have one, or sister, whatever. Okay, now let's come back to the concept of electronegativity. Right. So in this video we are going to discuss about a few examples that will clear up the concept of this electronegativity. Right. So first let's take an example of carbon bonded with oxygen. Right. So carbon will have 4 bonds, and let me just draw this big so I can show you where the electrons are positioned, and this is the electron. And remember, I'll do this in another color just in case. Okay, let me do that in blue. This is carbon. Let me do this in black. And this is oxygen. Right. So oxygen will of course have 2 bonds. This is one and this is another. Carbon will have 1, 2, 3, 4 bonds. Right? Okay. Now let's look at what happens to the electrons here. Right? So let's take another color. Let's say that, okay. So in order to know where the electrons are actually positioned, we need to know the strength of electronegativity or the value of electronegativity for each of these atoms, for this one and this one. Okay, now let's look at a scale which we discussed from last class, which is mostly used around the world, and it's called the Pauling scale, right? Okay, let's look at, I already wrote it down. Yeah, carbon will have 2.55, oxygen will have, let me just 3.44. Okay, now since we know these values, and I'll write it down to 1 decimal point. Okay, and this will be 2.5 approximately. This will be 4 according to the Paulink's electronegativity scale. Right. So what happens here? As you can see, oxygen has more electronegativity. That is, it has more ability or more power to take electrons or to keep electrons around itself for a longer time than carbon does. Right? It has the ability to attract electrons more than carbon does. Right? It has a much more stronger ability to attract electrons than carbon does. I know I'm repeating myself, but to make it clear to you. Okay. So since oxygen has more power or more electronegativity, the atoms right here, the electrons will be more around the oxygen than they do around the oxygen. We know that electrons are not exactly particles, but they are distributed according to their probability. So it's the electrons are most probably they are most probable to be found in this area than in this, right? Okay, now let's draw them if they were particles right over here, right? Let me use blue for carbon. This is an electron of carbon, this right here, if it was in this shape, and this is an electron of oxygen. Now since oxygen has a higher electronegativity, what happens is the electrons stay closer to oxygen than they do around carbon, right? So this is exactly what is called the phenomenon of electronegativity, or the property of electronegativity, right? So I'm going to tell you what makes a compound polar or not, polar, non-polar, and ionic. Here the electronegative difference is, as you can see, 0.9. This is considered to be polar, right? This is considered to be polar. Let me just write that down. So this is a polar covalent bond. There is no polar ionic bond, there is no non-polar ionic bond. There are only polar and non-polar covalent bonds. I will tell you the range as we move on. Okay. Let's take another example. Now let's take an example between carbon and hydrogen. And here's another thing that I want to tell you. Okay. If this is carbon and this is carbon, since they have 3.4, shouldn't have done that. Okay. Since they have electronegative values to be the same, electrons will stay somewhere in the middle. They are most probable to be found in both directions. If you want to check here, the probability, and here the probability of finding them will be the same. Okay, let me just do that. Okay. Now let's move on to the bond between carbon and hydrogen. I don't want to do more graphics, so let me just write it down simply. These are the bonds of carbon, and there is only one bond for hydrogen, since it can give away only one electron, right? So let's say this is the electron from hydrogen and this is the electron from carbon. Now let's check their electronegative values. Let's see. Let's go to hydrogen first. It has an electronegativity of 2.2, which is good. I don't know why I said that, but anyway. Carbon has an electronegativity of 2.5, as we already saw. Now this has 2.5. This has how much again? I'm sorry, 2.2. Yes. Now the difference here is really less. How much is it? 0.3, right? So you can consider this to be non-polar. This is non-polar. I will tell you the range, yes. Not right now. As we go on to the ionic bond, I will tell you the range of non-polar and polar covalent bonds. Right. Okay. Since we are near ionic bonds, so let's start. So let's take let's say what can we consider to be an ionic bond? Let's see. Okay, let's take a bond between carbon and let's see, sodium if you want to. Yes, carbon and sodium. Does that work? Do we have an electronegative value of sodium? Yes, we do. Okay. Okay. Let's say this is carbon right over here. Let's draw this with this. Let's go with blue because Na seems really cool. Okay. Now Na will have only one bond since it can donate only one electron. So what happens? I just checked and I saw that the electronegativity value of sodium is about 0.93, but I'm going to leave that 3 there. And carbon has an electronegative value of 3.4. Nice old friend. Is that it? Yes. No, I'm sorry. It's not 3.4, it's 2.5. Okay. Now the difference here, let's see, 2.5 minus 0.9. 15 minus 9 is 6. So you have an electronegative difference of 1.6, which is really big. I know you have 1,000, 1 lakh, so on in numbers, but when you consider a scale of electrons, atoms in the world of chemistry, this is really big, right? So this is this is an ionic bond. This right here is an ionic bond. Since this electron here, which let's say with the blue color, is completely given over to carbon, since it has such a high electronegativity than sodium, mind you, that it completely steals the electron. It doesn't even want to share. I'm sorry about no. Okay, I'm sorry about that. Okay, anyway, now I told you that I was going to tell you the limit or the electronegative difference limit for which bond can be polar, non-polar or ionic. Right, I'm going to write that down in the next page. Right, let me use a very special color. What can be special? A green would be nice. Okay. Electronegative difference. Okay. And also, if you spend time trying to stop the video at where I double click the home button, I'm telling you it's a waste of time. It definitely is. Anyway, now let's look at the electronegative difference limit for which the bond is a non-polar covalent bond. This is really, really important. In some places you might find other values, but it's almost always the same, right? Okay, now for it to be a non-polar covalent, it has to be from 0.0 to, that's actually 0, so I'm going to write 0 to 0.5 non-polar covalent bond. Right. So as you can guess, if it is from 0.5, starting from 0.5 to 1.7. Here we saw 1.6, but it's so close to 1.7 that we always consider it to be an ionic bond, right? Okay. This will be a polar covalent bond. If it is greater than 1.7, that's greater than, but let me just write it down correctly. Greater than 1.7, it is an ionic bond. Greater than or equal to ionic bond. See here, I drew something like this, right? I drew something like this. Let me draw it more clearly. Let me just 1 minute. Okay. Okay. And then you have the 4 bonds of carbon here, and then that's a little slanted. I'm sorry about that. Okay. Okay. As you can guess, this will have. Now, let me just draw this first, and then I'll explain. Now, this right here is not anymore a partial negative or a partial positive charge. It's a complete positive and a complete negative charge, right? This is important. Now it just can't be partially negative. It has a complete partial negative. A complete negative and a complete, this is completely positive and this is completely negative by 1 electron. Now if you were to have magnesium bonded to some other electron, you'll have 2 plus when it is grabbed by something else, let's say carbon for instance. Now this is important. It's not partial anymore. Carbon has completely stolen or completely taken away the electron. So this one doesn't have an electron. So what should it do? It should just have a positive charge and sit there until a negative charge. Wait, there is a negative charge here. So they both will get attracted, and they both will form an ionic bond. Right. Okay. So this is really, really important. Right. So sometimes people just keep it like this, but most of the time this is mostly used, right? So don't get confused if they just kept these signs, partial negative and partial positive. Anything is fine, but what is most important is it has now become completely positive or completely negative. You can say completely charged, right? I hope you understood today's lesson, and in the next video we'll be talking about intermolecular forces and intramolecular forces, which are really important. So hope you guys enjoyed the video. Thank you very, 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 very much.